In this unit, we're starting to investigate inequalities in absolute value. Today we're going to talk about what it means to graph a linear inequality. This spreadsheet is something that we did in class, so don't worry if you weren't able to participate in that activity. The first thing that we're going to do is for each inequality given, we're going to determine if an ordered pair is a solution or not. We're going to show our algebra. So we've seen this before with linear equations. We've also seen it with single variable equations. Here we just have linear inequalities. So you'll notice that the equal signs have been swapped out for inequality symbols. And then we're given this ordered pair that we're going to check if this is a solution or not. The way that we're going to do this is we're going to replace the x and the y with the variables given. So in example 1, I'm being asked to replace x with 10, and I'm being asked to replace y with 3. I'm going to do the algebra and see if my answer is less than or equal to 6. So I end up with 10 minus 9 is less than or equal to 6, 10 minus 9 is 1, and I can see that 1 is in fact less than or equal to 6. So that means that when I replaced x and y into my inequality, it created a true statement, which means yes, this is a solution. Pause the video to try example 2. Press play when you're ready to check your answer. Be sure to circle yes or no. So in this case, one thing to pay attention to is a lot of people make a mistake here. The inequality starts with the y variable, but remember the y variable is actually the second number in the ordered pair. So be sure that you're changing y to 2. This would become 2 is greater than 2 times negative 1 plus 5. Over here I can do my algebra, so I have 2 times negative 1, which is negative 2, and then I add 2 plus 5 to get 3. So the statement that I end up with, if I continue bringing down the 2 on the left, is that 2 is greater than 3. And since 2 is not greater than 3, this would mean no, that the point negative 1, 2 is not a solution to this inequality. Next, I'm just going to talk about what the difference is between an equation and an inequality from a graphic standpoint and a visual standpoint. So we've been graphing many lines like this, 4x plus 3y equals 24. We've talked about graphing lines using x and y intercepts, which would be the most efficient method here. We've talked about graphing lines using slope-intercept form and even point-slope form. When we graph a line, what the line represents is that only the points on the line would satisfy the equation. So in this case, if I were to find any of these points along the line and find their x and y coordinates and replace them in this equation, these points along the line would work. What happens when we change the equation to an inequality is two things. One is we notice we get this shaded region. Sometimes it's above the line, sometimes it's below the line. The other thing to notice is that sometimes the line remains solid and other times the line becomes dashed. So two things that our inequalities have in common are that always the points in the shaded region will satisfy the inequality. So that means on the center one here, if I were to pick any points from the shaded region and know their x and y coordinates, and then replace them into the inequality, any of these points within the shaded region would work. They would always be greater than or equal to 24. On this example over here, again, any point within my shaded region, if I were to find its x and y coordinates and then replace those numbers in this inequality, they would always be less than 24. The difference in these two inequalities is that this one is greater than or equal to, and this one is just less than. So when it's greater than or equal to, or even less than or equal to, the points on the line also count. So it's not only a boundary line, think of like painter's tape, but the points on the line will also satisfy the inequality if I were to plug them in. Whereas in this case, the line is only acting as a boundary line. The points on the line don't actually count. We just want to go right up to, but not quite the line. It's kind of like how when we graphed on a number line, we showed greater than or equal to or less than or equal to using a closed circle, but we showed greater than or less than using an open circle. It shows that we want to go right up to it, but not include it, and in this case, we want to include the line. Our next objective is to take linear inequalities and put them onto a graph. So there's three things that we need to do. The first thing is that we need to get the points that would be on the boundary line. The second thing is we need to decide whether we want to do the boundary line as a solid or a dotted line. And then the last thing is we want to shade in one side by picking a test point. So we want to be efficient when we're graphing our lines. Again, there's three ways we can graph our lines, either slope-intercept form, x and y intercepts, or point-slope. Most people tend to pick between x and y intercepts or slope-intercept form. And you want to think like an efficient mathematician. So what I notice on example 1 is that since y is already isolated, I'm going to graph this as if it were the equation y equals 4x minus 3. So if I remember my slope-intercept, that means first I'm going to start at my y-intercept of my b for begin, That's always going to be on my y-axis. And then I'm going to rise and run to my next points on the line. So that means I'm going to rise 4, 1, 2, 3, 4, and run 1. And remember, when you're rising and running, you're starting from your previously graphed point. And I'm going to do that as many times as will fit. Now, before I connect with a line, I next want to determine if that line should be solid or dotted. So this is where I'm going to forget about the fact that it was an equation, and I'm going to go back to my inequality. So in my original problem, the inequality was greater than. So that means that it can go right up to the line, but not be equal to the line. And the way that I'm going to show that is I'm going to use a dotted or a dashed line. Now, I'd still want to use a ruler if I was on paper, but it's a little difficult on Explain Everything. So I have my boundary line, and it's dashed, showing that this is just going to separate the shaded side from the not shaded side, and the points on the line would not actually satisfy the inequality. The next thing that I'm going to do is I'm going to shade one side by picking a test point. Of all the points on my graph that might be available, the easiest one to use is 0, 0. And in this case, it's available since the line does not pass through it. So in this case, I'm going to replace x and y both with 0. So that would give me 0 is greater than 4 times 0 minus 3. 0 is greater than negative 3. Now 0 is greater than negative 3. So what that means for me is that the origin is part of my solution set. It would work if I were to plug it in, or it did work, in fact, when I plugged it in. And so the other solutions are located on the same side of the line as the origin. So that means I'm going to shade all the way up to this line, and that's going to be my answer. So my answer is the graph, it's the picture. And so what this is telling the reader is that any points within the shaded region are solutions, and the line does not count. Let's try example 3, and then you'll do 2 and 4 on your own. So on example 3, the first thing that I want to do is I want to graph my boundary line. Now in this case, since it's in standard form, y is not isolated, I'm going to graph it using x and y intercepts, and I'm going to graph it as the equation x plus y equals negative 1. Now to find an x-intercept, I change y to 0. So I'm going to start by doing x plus 0 equals negative 1, x equals negative 1. So that means my x-intercept is the point negative 1, 0. To find my y-intercept, I'm going to change x to 0. So 0 plus y equals negative 1, y equals negative 1. And as an ordered pair, that's the point 0, negative 1. Now that I've graphed my boundary line, I could do a couple things. One is I could add some more points if I wanted to. You don't have to, but I want to make sure I have a nice full line. And it's going to be hard for me to do this on Explain Everything. So one thing I notice is I can see, okay, to get from one point to the other, it's up 1 over 1. So I actually am going to graph some extra points, like I said, just because this will help me connect, especially on Explain Everything. Now I'm going to refer back to this inequality here, which is greater than or equal to. So because it has the or equal to, this means that the line isn't just a boundary line, but that the points on the line also count as part of my solution set. So I should have a straight edge. That feature isn't readily available here in Explain Everything, but I should be connecting those points with a ruler. So if this had just been a linear equation, this would be my answer. But because it's an inequality, I want to show the other parts where the points are that are parts of my solution. So my test point in this case, again, can be 0, 0. The only time you can't use 0, 0 is if the line passes through it. So I'm going to go back to my original inequality. I'm going to replace x and y with 0, and that gets me the inequality 0 is greater than or equal to negative 1. And that is true because 0 is greater than negative 1. So that means the origin is part of my solutions, and so this side of my graph is where all my solutions are located. So my picture will be my answer, and what the picture is saying is that any point from this shaded region, or because my line is solid, any point on the line will also count as part of my solutions. If I were to plug them in here, they would work. So at this point, you're going to try examples 2 and 3. When you graph each line, be sure to choose the most efficient method, either slope-intercept form or x and y intercepts. Don't forget to think about what line type you want, solid or dotted, and then choose your test point and test to see if it is part of the solution set. Now in both of these cases, the origin worked, so I was able to shade with the origin, but if the origin didn't work, I just would have shaded the other side. Pause the video, press play when you're ready to check your answers. So on example 2, it makes the most sense to graph as a slope-intercept equation. So you're going to, in your mind, you're going to treat this as if it were just y equals 3x plus 1. That means you're going to start at plus 1 on your y-axis, and then you're going to rise 3 and run 1. and then I did some in this direction as well. When it was time to do my boundary line, I looked at my inequality and saw that it was greater than or equal to. So that means my line is part of my solution, so I made that a solid line. And then the last thing that I did was I picked my test point. I chose the origin because it was available, which means I was going to replace both x and y with 0. And what this ended up with was 0 is greater than 1 when I did out this algebra. Now 0 is not greater than 1. So what that meant is that the origin was not part of my solution set, so my solutions are on this side of my line. For example 4, I graphed it as if it were the equation x plus 3y equals -6, and I did this using x and y intercepts. So to find my x-intercept, I made y 0, and my x-intercept was -6. That means it's crossing the x-axis at -6. To find my y-intercept, I made x 0, and then to get y by itself, I divided both sides by 3 to get y equals -2. This meant it was going to cross my y-axis at -2. Again, I chose my origin, which meant I replaced x and y with 0, which created this inequality 0 is less than -6. That is not true, which means the origin is not part of my solutions. So I shaded below. The last thing I'm going to do in this first set of notes is I'm going to take the graph of an inequality and create the inequality. So we're essentially working backwards. It's kind of like writing a slope-intercept equation, but doing it with an inequality. So because of that, the first thing that I want to find on this graph right here, or the first thing that might stand out to you, is perhaps that the line is dotted. So what that would tell you is that your inequality is either going to be greater than or less than. I next notice that it crosses the y-axis at -3. So that means I have a b value of -3. I might then put another point here to calculate my rise and run. My rise is 3, my run is 3, rise over run, which means my slope is 1. So I have a b value of -3 and a slope of 1. So if this were being asked for a linear equation, my equation could have been y equals 1x minus 3. But since two things stand out to me, one is that it's a dotted line, but the other is that it's shaded, I know that it has to be an inequality. So in this case, what I would do is I might pick the origin, 0, 0, and what I see about the origin is that it's not in the shaded region, and so that means I need to make it so that way the origin is false. So I'm going to change y to 0, I'm going to change x to 0, and I'm leaving this as just a blank space for right now that I'm going to come back and fill in later. And I'm either going to fill it in with my greater than or less than symbol. What's going to be a little bit hard for my brain is I want to make sure I pick the one that makes it false, because the origin is not in the solutions, because it's not in the shaded region. So I'll come back here, I've got 0, then my blank space. 1 times 0 is 0 minus 3, and so then I have 0 being compared to -3. And so I know that 0 is bigger than -3, so I'm going to write it as 0 is less than -3, because I want it to be wrong, because I know the origin is in the wrong side. So I'll come back to my equation that I wrote, I'll erase my equation, and then I'll replace it with my less than symbol. So the inequality represented by this graph, which had a slope of 1 and a y-intercept of -3, it was a dotted line, is y is less than 1x minus 3. And again, that less than came from the fact that my origin, if I replaced it, then on one side I had 0 and on one side I had -3, and I needed this to be a false statement. And the true version, if I start with that, was that 0 was greater than -3, so the false version is that 0 is less than -3. Pause the video to try example 6. Some things to look out for is what kind of line do you see, and so what will that mean about your inequalities? Be sure to find the slope and the y-intercept and start with an equation. Then think about your test point and whether or not you want that to be true or false. In the end, your answer should look something like this. Y is less than 1x minus 3. Pause the video, press play when you're ready to check your answers. So on this example, I noticed that the line had a y-intercept of 3. I also noticed that it had a negative slope. So my slope was negative, and then rise of 2, run of 1. So my slope was -2. So as an equation, it would have been y equals -2x plus 3. Because the line was solid, I knew that that meant my inequality was either going to be greater than or equal to or less than or equal to. So I used my test point of 0, 0, which meant I replaced y with 0, and I also replaced x with 0. And I have this empty space here to fill in for my inequality. Because the origin was in my shaded region, that meant that I wanted my origin to create a true statement. So on the left side, it ended up with 0, and on the right side, it ended up with 3. To make that true, picking from these two inequalities here, I chose less than or equal to. So 0 is less than or equal to 3. So as an inequality, y is less than or equal to -2x plus 3.